Okay, so for the design of singly reinforced concrete beams using the Strenght Design Method, so I have established here a steps, no? This is just one of the steps that you may use, no, in the design. But if you're going to look at other reference, no, other authors, so they have actually presented a different way of designing, no, a singly reinforced beam. So they have actually already established, no, their own method on how to design, no, a singly reinforced. Ako nga, meron din akong ibang procedure, no, kapag nagdi-design ako ng beams. I'm not doing this enumerated steps, no, but then again, you should know this, no, because it is the basic, no, so it is actually a basic way of designing a singly reinforced beam. Okay, so let us look at the given and unknown, no, when you design a singly reinforced beam. So number one, ang given is the so when you're dealing with a given problem, no, so then you are required to design it, no. So it depends, no, kung ang given ay load, so you're going to solve for the moment. Okay, there are other problems wherein you're going to determine how the load is being distributed to the beam, no? Merong mga ganun na problem. So ibibigay niya yung mga loads, then merong isang floor plan. Okay, nakalagay doon yung beam, no, beam framings, no, doon sa floor. So meron kang mga slab, then the loads that are being carried by the slab nakalagay, and all you have to do is solve how this load is distributed to the beam, no? So doon mo palang kukunin ngayon yung load na kine-carry ng beam. So merong mga problem na makikita sa mga books na ganyan, no? Okay, ngayon once you have the load, ang gagawin mo ngayon, isosolve mo yung moment, no? So yung pagkuha ng moment, yun ang mga pinag-aaralan nyo sa theory, no? Kung indeterminate or determinate yung system mo, you should know anong method ang the best mong gamitin, no? So yun yung purpose ng theory, no? So kung ano yung knowledge na nag-gain mo doon, yun ang gagamitin mo to get the required moment. Okay, so moment, so yun ang pinag-uusapan natin dito. So ngayon, when you design, you should have a known moment. So yun yung kukunin mo. So usually, kino-consider natin yung mga maximum moment. So merong mga beams na meron siyang negative moment, merong beams meron siyang positive moment. Okay, so you have to consider those, no? So what is the maximum positive? What is the maximum negative? Or it depends on their location, no? So doon mo siya kukunin or i-design. Okay, so yun yung about moment design known. Pag moment design ka natin, we're talking of the factored moment, no? Okay, and this is already the maximum, meaning it is based from load combination, no? Kung meron kang dead load, meron kang live load, meron kang iba pang mga load, no? So you need to consider those load combination. And remember, in Strenght Design, yung mga loads natin naka-multiply ng factor. Kaya ang tawag natin ay factored load, no? Okay? Kaya itong moment natin ito is considered as a factored moment. So, yun ang kukunin mo. Now, ano yung mga unknown, common unknown sa beam, no? O sa problem. Unknown yung width, unknown yung depth, unknown yung reinforcement. So, those are the common unknown sa mga problem. Unknown yung width ng section ng beam, unknown yung kanyang depth, no? Unknown yung kanyang reinforcement. Okay? So those are the things that you need to look at, no, kapag nagdi-design ka. Okay. So we're going to derive now yung useful formula, no, in the design of singly reinforced beam. Okay, so for the derivation, just like in the analysis, we're going to make use of equilibrium, no? So we're going to apply equilibrium, then we're going to assume that the steel is yielded, no? So making use of these useful formulas, okay, for the depth of the compression block, then making use of the steel ratio, rho is equal to AS over BD, and then if we will isolate AS here, we have the formula rho BD. So if we will substitute this in the equation for the compression block, for the depth of the compression block, our depth of compression block now will be equal to rho D Fy all over 0.85 F prime C, no? So yung ating B canceled out na, no? Next. Okay, so we're going to equate these two equations. The design moment, which is based from your factored load, and your moment capacity. So Pmn is your design moment strength, or this is your strength capacity of the beam. So we're going to equate the two. So when you analyze, your Pmn must be greater or equal to Mu. Okay, yun ang condition para masabi mong safe, no, yung beam mo, no? But here in the design, we're going to equate them. So our Pmn is equal to Ph(Fy) multiplied by D minus A2. So you're going to equate this to Mu. And then As, okay, based from our equation here, As is rho BD. So substitute natin rho BD. Okay, and our A is rho D Fy all over 0.85 F prime C. So substitute lang natin dito. Then if we will simplify this, we have the equation Mu equal to Phi rho Fy by the quantity 1 minus 0.59 rho Fy over F prime C multiplied by BD square. Okay? So where rho is specified by the designer. Ito, no? Pag ikaw ang designer, you're going to specify this. Now, yesterday, I have given you an idea when you assume a value of your rho, it should be equal to 0.4 to 0.5 of rho max. No, I think I have given that, no, or rho balance, no. So let's look at that, no. So tingnan natin uli yun. Okay, when you assume a rho, no, equal to that quantity, Okay, you're going to limit, no? You're going to limit the cracks and the deflection. That's the advantage of using that recommended value of your raw. Ayun, no? So I think ito yung value niya. 0.4 to 0.5 raw balance, no? So that is what is recommended, no? For you to limit cracks and deflection. By the way, cracks and deflection are serviceability requirement. When you design your beam, you need to check this. But again, if you will make use of this value of raw, which is equal to 0.4 to 0.5 raw balance, so you may limit the cracks and deflection. So meaning you don't need to check, no, cracks and deflection, or you don't need to check serviceability requirement, no? So yun yung pwede mong gawin. But then again, to be safe, even though it is mentioned, no, that you may limit cracks and deflection, i-check mo na rin, no, para sigurado ka, no? Check mo na rin yung cracks and deflection. Okay? So yun ang pinaka the best mong gawin. Okay, so that's about raw, no? It is specified by the designer. So actually ito, it depends on the experience of the designer, no? Kaya nga yung pagdi-design, kailangan may experience ka, no? Ano yung experience mo? Construction, and then you also somehow already designed some structure in you actually investigate, no? You already investigate that making use of this value of raw, you may able to limit cracks and deflection. Now, yung cracks and deflection na binabanggit ko na malilimit mo, it is based from code. Kasi yung code meron siyang limitation, meron siyang allowable, no? Not really allowable itself, but limit, no, for you to say na the cracks are controlled and the deflection are controlled, no? So meron ganun yung code at pag-aaralan natin yon. Okay, pag-aaralan natin, no? Okay, how do we predict, no, na yung cracks, no, yung possible cracks, no, na pwedeng yung size ng cracks due to the load, no, and due to the given dimensions and reinforcement for your beam. So how do you predict it, no? And also the deflection, no? So how do you predict it? So napag-aaralan yun, okay? So na-compute natin, no? Okay, so yun yung about this, no? You need an experience for you to know kung ano yung pwede mong i-assign na raw. But we already have based from the one that I have presented yesterday. So we already have an idea, no? What will be the value of raw, no? When you design, no, for you to limit cracks and deflection. Okay, so once you have your raw, okay, to simplify this resulting equation, no? Okay, we equate a certain quantity here, no, in terms of a single quantity, no? Okay, so that is the value raw Fy multiplied by the quantity 1 minus 0.59 raw Fy over F prime C. So we equate this to a certain quantity, a single quantity, R. And then, if that is equal to R, so the result, our mu now is equal to phi R BD square. And look at our equation. Okay? Unknown to BD. Because mu is computed, no? You have your BD, no? Remember your R is based from your raw, your Fy and Fc prime. These are what? These are assumed by the designer. Ikaw ang ikaw na designer ang magdi-decide kung ano yung strength ng concrete mo, kung ano yung strength ng bakal na gagamitin mo. But then again, for the strength of the materials, you are also guided by the code, no? Kasi merong recommendation yung code. Kapag ganito yung size ng bakal mo, kailangan strength. No, merong mga recommendation na ganyan ang code. And even the strength of the concrete. For beams, columns, no? Kailangan ganito yung strength ng concrete mo, no? So there are recommendation by the code, okay? Kaya hindi ka mawawala, no? So this particular R can be easily compute as long as you have your F prime, Y, and rho. Then eventually your equation will be unknown to BD. Now B is known as the base, D is the effective depth. No? So isolating BD square now, you have your equation BD squared equal to mu over phi r. No? Now, when you solve the dimension of your beam, no? So this is how you do it, no? So you may solve for B and D. This will require an assumption on one of the two or on their ratio. So meaning, for you to have B and D, you need to assume one of this, no? Okay? You may assume B equal to ganito, then you solve for D. So that is the one way of doing it. Or you may express the two in terms of a ratio, no? So those are the assumption made by the designer, no? Kapag nagdi-design ka, no? Okay? Then once you have your B and D, you may now solve for the area of the steel. Okay? So pag meron ka ng area ng steel, makukuha mo na yung number of reinforcement. Ilan ba yung bakal na kailangan niya? So kukunin mo na. Then once you have now your section dimensions, you have already your number of rebar. So ang susunod mong gagawin ay you investigate your beam. So babalik tayo sa analysis, no? Okay, babalik tayo sa analysis. You're going to check now the adequacy. Okay, yung bang dinesign mo, kaya ba niyang i-carry yung load, no? Nung yung beam. Okay? So, yun yung procedure natin. Okay? So, let us look at now yung example problem natin, no? Nakikita na ba yung ating example problem? Hello? Nakikita? Okay.
Yes, sir. Nakikita po.
Okay, so we have a simply supported beam, no? Okay, ito yung pinakamadali kasing example natin para kaagad makakuha tayo ng maximum moment. Okay? The length of the beam is 4.5 meters. And then the dead load, which is unfactored, 18.5 kilonewton per meter. The live load, also unfactored, is 35.6 kilonewton per meter. Okay, the strength of the concrete is 21 megapascal. The strength of your steel is 276 megapascal. Okay, ito ngayon assumption natin sa ating raw. Raw is equal to 0.5 raw balance. So we follow yung recommendation o yung suggestion, no, na raw value natin na pinakita ko sa inyo kahapon. So 0.5 raw balance. Okay, so these are the designation ng ating mga given values, no. L is the length of the beam, DL is the dead load, live load, LL is the live load. Then I also specify here that our tie bar is 10 millimeter and our concrete cover is 40 millimeters, no? So those are the given in the problem. Okay, so now for the solution, we're going to solve for the maximum moment, no? Okay, so since we need, no, a load combination and the load must be factored, so making use of the NSCP. So walang naka-indicate dito, no, but this is NSCP. Okay, NSCP 2015, no, because NSCP 2015 already adopted the new code, no. That is the 2002 code, yung ating NSCP 2015. Okay, so the factored load, and it is this is already the load combination. Okay, so for dead load and live load, so dead load we multiply it by 1.2 and the live load by 1.6, and the combination 79.16. So I think in the book, in the NSCP, meron tayong combination doon na 1.2 dead load lang. So sigurado tayo mas maximum ito, because in the load we select whichever is the maximum, no? So ito yung maximum load natin, maximum load combination. Okay, so since simply supported yun, yung formula for the determination of the maximum moment is WUL squared over A. So napansin nyo dito, meron na subscript na U. Okay, actually ang tawag nga nila dyan ultimate, no? Dahil dati ultimate strength method dito, no? So yun ang tawag nila noon dyan, ultimate load ka natin, and the moment is known also as the ultimate load, no? Okay, so ito yung maximum, and we have a positive moment. So therefore we're going to design yung tension reinforcement natin, which is located at the bottom, no? Located at the bottom of the beam, no? So nasa baba, wala siya sa taas, no? Kasi ang curvature nito ay concave upward, kaya yung tension natin nasa baba, ang compression natin nasa taas. Okay, so this is now the design moment, 200.374 kilonewton meter. Okay, so ito ngayon yung step natin. We assume that rho is equal to 0.5 rho balance, and the formula for rho balance, we have this one. Okay, so we need beta 1. So beta 1 is 0.85 since our F prime C is 21, no? So then our rho is 0.019. So we're going to use this now to solve for R. So 4.438. And we're going to substitute this in our equation. BD square equal to mu over VR. Okay, so ang ginawa dito, nag-assume tayo ng width ng section, which is 300, and we assume that our our section will be tension control, 0.90. Okay? So para pag sinolve natin yung D, no? Okay, we have 408.948. Now, yung D natin dito, no? Kung titignan yung mabuti, no? I equate it to 434, no? Bakit, no? Initially kasi, no? Yung mga section natin, yung mga depth, ano yan, no? Multiple of 50, no? Multiple of 50. So kung 408 yan, ang magiging possible depth natin ay nasa 450 or 500. Those are the two choices, no? Kapag namili tayo ng depth, no? Now, ang ginawa ko ngayon dito, no, ay initially, no, solve yung effective cover. Ano yung effective cover natin? Concrete cover plus tie wire plus, no, yung ating diameter, no? I'm assuming that yung ating reinforcement isang layer lang yung ano natin. So I'm assuming the diameter of bar na gagamitin ay 32. So you have there 66 ang effective cover. Kapag inad natin ito sa 408, if you look at yung initial computation ko dito, no? Kikita nyo dito 408.95 plus 66 is already 475. So ibig sabihin lumagpas ka na ng 450. So yung 450 is no longer a choice, no? Kundi yung 500 na, no? Kaya ang gagawin mo ngayon, you equate this to 500 and then you subtract 66, which is your effective cover. And the result is 434. Ayan. Kaya yung magiging effective depth mo ay 434 millimeters. So, ganun kapag nagdi-design ka, no? Okay? So, ngayon, once you have your D, which is equal to 434, and B is 300, you may have now your area of the steel. Area of your steel is raw BD. So, 2,451.19 or 186 square millimeter, no? Okay? So, ganun kapag nagdi-design tayo, no? Okay, so once you have your required area of steel, since we already assume a diameter for our reinforcement which is equal to 32 millimeters, so we're going to solve for the area of the 32 millimeter diameter bar, no? And that is 804.248 square millimeters, no? Then, ang gagawin mo, you're going to solve for the number of bar. So, the number of bar can be computed by taking the ratio of the required steel and the area of the 32 millimeter diameter bar. And the result is 3.048. So, I decided to use 3. No? Ayan. Okay, so decided to get 3. Now, meron tayong figure dito para makita nyo kung ano yung effective cover. Ito, ano? From the bottom of the beam, which is under tension, hanggang do sa centroid ng layer ng bar, no? So, yun yung concrete cover natin, no? Concrete cover plus tie bar plus bar over 2. Okay? So, ngayon, I decided to use 3 instead na 4. No? So I decided to use 3, no? Okay, so therefore, I will check now the spacing of my bar kung nasa-satisfy ko yung code requirement na minimum of 25 millimeters, no? Ang clear spacing. So I'm assuming now that the 3 bar are located in a single layer, no? Naka-single layer lang yan. So ngayon, ito yung checking natin, no? Consider 1 layer of bar. So the clear spacing of the bar, ito yung pinaka-formula natin, no? Yung width o yung base, no? Yung width ng ating section minus concrete cover plus tie bar. So yung nasa gilid. Meron kang clear spacing dito, tapos meron kang tie bar, kaya naka-multiply siya ng 2. No, dahil on both side yan. Aalisin mo muna yon, no? Alisin mo yon. So ang matitira na lang ngayon, magbuhat dito hanggang dito. So ang gawin mo ngayon, alisin mo yung mga bar mo, no? Kaya N minus N dB. So ang matitira ngayon dyan ay yung space between bar. So how do you know now na ilan yung clear space ng bar? You divide all of this by N minus 1 because the spacing here or the division or the space here between bar is actually equal to 2. Kung 3 yung bakal mo, ang space mo 2. Ang clear spacing mo, no? Kaya naka-subtract siya ng 1. So yung remaining space here, i-divide mo siya ng 2. And that will be your clear spacing between bars. And the result is 52 millimeters. So, and this is greater than 25 millimeters. So therefore, okay yung bar mo in a single layer because you satisfy the minimum code requirement na 25 millimeter clear spacing. Okay? So then, no, you already design now your beam. Meron ka ng design, meron ka ng section, meron ka ng number of bar, no? Ang susunod mong gagawin ngayon, you check for the adequacy. Okay, you check the adequacy. Wherein you go back to analysis, no? Ano yung assumption natin? The reinforcement yield, okay? And your A is 124.354 millimeters, no? And then you solve for C, okay? And your C is 156.299. So nakikita nyo dito puro shortcut na, no? But remember, when you do this in an exam, you should complete it, no? Kailangan well presented to, no? Kompleto, ha? So I just shorten, no? Dahil yung MATCAD kasi kaya niyang gawin yan, no? Okay, you check now if your steel really yields, no? Okay, so it shows here that your FS is 1,179.915 megapascal. And this is greater than Fy. Ano ba yung Fy natin? Ang Fy natin ay malayo-layo, no? Malayo-layo na tayo kasi, no? Dito na lang tayo. Okay, yung Fy kasi natin ay 276. Okay? So therefore, our Fs is greater than Fy. So our steel as yielded. So tama yung assumption natin dito na nag-yield yung steel. So therefore, your A and C are considered correct. So therefore, assumption is correct. No? Okay. Now for the design moment strength, no? So we need to solve for the strength reduction factor. So using NSCP 2015, let us solve now epsilon t, the net tensile strain. We need to determine d sub t, and d sub t is equal to t. Since this is the we have only one layer of bar, no? So the net tensile strain is 0.005 or 59, no? Okay, pag nag-round off tayo, 0.059, okay? And this is greater than what? Greater than 0.004. So 0.004 is the criteria for us to identify if our design is ductile. So lumilitaw ductile, no? Yung ating design. Even though pinili natin tatlo lang, no? So ang design natin ductile. So magandang ano to, no? Magandang balita to, no? Okay, so after knowing that our design is ductile, we may now solve our strength reduction factor. And it shows here that epsilon t is greater than 0.005. Therefore, our section is tension control. No? So we have a tension control section. So our phi now is 0.90. Okay. We may now solve PMN. No? PMN is solved, and it is equal to 222.84 kilonewton meter. So this is now the strength, no? Ito yung pinaka-strength ng ating so ito yung pinaka-strength ng ating design beam, no? Ang kanyang capacity nasa 222.84 kilonewton meter. Now, if we will look at yung given problem natin, okay, dahil nagdi-design pa lang tayo, wala tayong weight ng beam, no, do sa computation ng design moment, no? So since we already have the dimension of our beam, so we may now compute, no, the additional weight that will be added, no, dun sa ating computation ng ating design moment. Okay, so we need to include the weight of the beam. So the computation, we get the area of the beam of the cross section, and we multiply it by the unit weight of the concrete, which is 23.6 kilonewton per cubic meter, no? So ito ngayon yung computation natin. Ang weight ng beam natin per unit length is 4 kilonewton per meter. Okay? So it will be added do sa dead load, dahil dead load yan. Multiply natin ng 1.2. Then yung live load natin 1.6. This is now the final load that is acting on our beam, no? Okay? So included ngayon yung weight ng beam natin. So then, no, we will solve the maximum moment, no? So this is the design moment or maximum moment, wherein we include the weight of the beam, and the result is 211.126 kilonewton meter. And the design or the factored design moment or the factored moment strength is actually greater than MU. Okay, so yung capacity ng beam mo mas mataas kesa dun sa moment na ibibigay ng beam mo, ay ng mga loadings mo. So therefore, we can say the beam is adequate, no? So kaya niyang i-carry yung load because its capacity is greater than the load or the moment produced by the load. Okay. So then, no, if this is if the strength is greater than the factor or we have the design moment, therefore the beam is adequate. And the last part, you're going to present the drawing of your section, no? And this is located at the midspan. Sa midspan ito, no? Okay, this is located at the midspan kung saan nag-occur yung ating maximum moment. Okay, so yun yung ating pinaka-sketch. Okay, so yun yung procedure sa design ng singly reinforced beam. Okay, question? Meron kayong tanong with regards to the procedure? Okay. Meron kayong tanong. So if you look at other books, they have actually a different procedure, no? Sa design, no? May kanya-kanyang ano lang sila, no? Procedure. But actually, I'm using the basic procedure, no? Which is ito yung common na procedure, no? If you read the book of, I think, Nilsson, no? Si Nilsson, meron siyang ibang procedure, no? Okay, meron siyang iba, no? Pero nagbigay siya ng ano, ng ganito, no? If I'm not mistaken, a basic procedure like this, no? Si Nilsson. Okay, so that's why I'm encouraging you to read, no? To read books. So nakita nyo, no, kung ano yung mga adjustment na ginagawa mo kapag nagdi-design ka, no? Makikita mo yung effective depth mo. Okay, bago mo kinuha yung area ng steel, you already adjusted. You already adjust effective depth. Okay? So, meron kayong tanong? Meron? Okay, wala, no? Let us proceed. Okay? Okay, kung wala kayong tanong, so let us proceed to the next topic. Anong oras na ba? So, 1:14, no? Break tayo ng Break tayo ng 15 minutes before I proceed to the analysis of doubly reinforced beam. Okay, so break tayo ng 15 minutes, balik kayo ng 1:30. Okay? So, break muna tayo.